Problem 6. All right, what do we got here? We have the rise or fall of a liquid in a small diameter capillary is not affected by which of these four things? We had adhesive, forces, all right then, don't like that word, that's fine. Adhesive forces, cohesive forces, surface tension, or fluid viscosity. So rise or fall of liquid in a small diameter capillary in a capillary tube is not affected by which of these? This was one you may have learned in the fluids lab if you took it here. For this one, there actually is an equation by the name of the height of capillary rise in terms of sigma and beta gamma diameter. For sigma, cosine of beta divided by gamma diameter. So, as you can see, what is not in this equation that we have on our answers? We have no account of our fluid viscosity. Fluid viscosity being, kinematic being that, and dynamic being this. Neither of those are at all in this equation. So we can say, since sigma is surface tension, beta is contact angle, beta, and gamma is the specific weight. D is the diameter of the tube. So the first two choices, adhesive and cohesive forces, they will depend on the diameter and or specific weight of the fluid. So both of those we know can't be the answer because they're incorporated into these two. Also, the contact angle may also be a player in that regard. Surface tension, we have a direct surface tension contribution from the sigma term. So that basically leaves the fluid viscosity, which is not appearing in this equation, to be our answer, and that is the answer choice is D. Oh, right, very nice. Again, if you guys have any questions, please submit them in the comments below. I'll do my best to get to them. And if not, I hope these are beneficial to you. We're going to move on now to section 8, being fluid statics, and we're going to do some problems here. We're going to start with problem number 1. This is going to be S8, fluid statics. Okay, we have a barometer that contains mercury with a density of 13,600 kilograms per meters cubed. We have atmospheric conditions, 95 kPa is our pressure. Our temperature is 20 degrees Celsius. And we have a vapor pressure. Vapor pressure is really small, 0.173 kPa. Column of mercury will rise to what height most nearly? All right. How high is our mercury going to rise with these conditions on our tube? Okay. So what we want to look at first is the general equation for fluid rise, or for pressure. How do we balance our pressure? PA is equal to P, I guess this is just whatever your secondary point is, plus rho GH. What we want is H. Yeah, so we can solve for H and get PA minus PB divided by rho G. Our pressure at A point is going to be here, where we have our 95 kPa. And our secondary point, our vapor pressure, is going to be our pressure at point B. This is PI. Initial pressure, we'll call it. Or I'll just say PA. Our rho G, we have rho here, and G is going to be gravity. So if we have all this information, 95 minus it's actually 95.8, but that shouldn't make too much of a difference. 95 minus 0.173 divided by 13,600 times 9.81. This will give us around 0.718. meters. One thing I did forget to mention up here at the top, we have to change our pascals into kilopascals, so this is going to be a 1,000 factor up here multiplied to change this to pascals, since that is necessary. It's going to be a little much bigger on the top, which is this answer is most closely resemblant to 0.72 meters, which is answer choice C. All right, there is that problem done. Next problem we are going to do, let's look at number 2. We have a manometer. Okay, we have our tank here on the left, tank A. Gonna go down like this. Tank B is over here. One meter, 0.5 meters, we have two different types of fluid in here. We have a specific fluid starting from here, going down and stopping at this point. Another one here. And then water up here. This is number 0.1. This is 0.2. This 0.1 is referring to the level at which this liquid, which is glycerin, is at. Two is this point here where it separates. 0.3 is here. And then 0.4 is where the water is sitting. This is up here. All right, wow. Quite a diagram, don't we have? Liquid number 1 is water, liquid number 2 is mercury, liquid number 1 is glycerin. Let's see. What most nearly is the difference in pressure between point A and B? We want to find the difference in pressure between this point and this point. Okay, we have Sg of mercury, 13.6, and then the Sg of glycerin, 1.26, and water is water. No Sg's for water because it's water. All right, what is the pressure difference? All right, okay, how do we deal with this? So the pressure at level 2 is going to be the same in both the left and the right legs of the manometer. 0.2 here. This pressure here, here is going to be the same as the pressure over here. So with that, we can write an equation. P2 equals P at point A plus rho of water GH of 3 H3 minus 4 plus rho of mercury times GH2 minus 3. This is the left leg of the manometer. Left leg is this one over here. We have A. Pressure at A going down plus rho of the water times GH 3 minus 4. 3 minus 4, this distance here, pressure here. Also adding P of the mercury times, rho of the mercury. These are all rhos. That's not a rho, just these two. G times H of 2 minus 3. This minus this distance. So if we want to get this distance, it's going to be 1 meter minus 0.125. That'll be the left leg. Now let's do the right leg. P2, again P2 starting here, is equal to PB plus rho G times, let's give me some more space, rho G times G H of 1 minus 2. H of 1 minus 2 for this one will be this height here, 0.5 meters. Fortunately, it gives us all these heights. It's really convenient. Okay, so now that we have all of this, what is it we are actually looking for? Pressure difference between point A and point B. Finding these two then. All right, let's not worry about that. So, PA, we can continue on. If we equate these two, minus PB, because the pressure difference, is equal to G times, let's continue down here. Actually, I may not have enough room. Rho G, H of 1 minus 2, minus rho of the water, H3 minus 4, minus rho of Hg, which is mercury, H2 minus 3. Alright, so with this, what do we got? We know we have this term, we have the rho for everything, and we have all the heights. So we can find and calculate the pressure difference. The only thing you do have to take into account is the units for this. If we want kilopascals, we're going to need to multiply by a factor. So let's just continue through this. G times the rho of water times our Sg of glycerin, H1 minus 2, minus Sg of water, H3 minus 4, minus Sg of mercury times H2 minus 3. Sg of water is just going to be 1. So this is going to be 9.81 times 1,000 kilograms per meters cubed times, okay, I'm going to write this down here, after what's a 1.26 times 0.5 minus 1 times 0.125 minus again 13.6 times 1 minus 0.125. This will come out to about negative 111,785 pascals, or 110 kilopascals, which is most closely resemblant to the choice D. Okay, that was a bit of a long problem. But what we did in this problem is equated the right and the left leg. Since we're looking for something in reference to the right and the left leg, we equated the pressures building up to this point here where they're equal. Having this equivalency point here was very important because it allowed us to relate the two sides. So and then after you do that, it's pretty easy to figure out what you need and what you don't have. It's just making sure you get the units right and all that. So answer choice D would be the solution for this one. Okay, let me see if there's any more I can do that are short. Running low on time here. Let's see. Most of these are pretty long. Let's look at number 3. Problem number 3. An open water manometer is used to measure the pressure in a tank. The tank is cylindrical with hemispherical ends, and the tank is half filled with 50 kilograms of liquid chemical that's not miscible with water. The manometer tube is filled with liquid chemical up to the water. All right, we have a thing, looks like a pill. We have water up to a specific point in that pill. The pill is 10 cm. Not 10 cm, 10 meters. And the, what is this? Radius of this hemisphere or semicircle is 2 meters. We have a manometer. Like so. Filled about this height. We have a chemical here up until this point, and then the rest is water. Water is up here to down here. This section is 400 millimeters. From here down 225 millimeters, and from here is 50 millimeters. What is the most nearly the pressure in the tank relative to the atmospheric pressure? Okay, what do we have to do for this one? So what we have to do, we got to get the density of the chemical from the volume and the mass. So let's figure this out. Total volume is going to be equal to 4/3 pi r cubed plus pi r squared times, it's going to be times L minus 2r. Okay, so this is the total volume of the tank. We have the volume of the two hemispherical ends and then the rest of the cylinder. That's what this equation is representing. This is going to be equal to 108.9 cubic meters. The contents have a mass of 50 kilograms and the tank is half full. So let's get the density of the chemical. Mass over volume. 50,000 kilograms divided by 1/2 times 108.9. This comes out to 918.2 kilograms per meters cubed. So now that we have this information, we can go and find the relative pressure. P0 minus P2 is equal to the rho of water, GH2, minus P of chem GH1. If you need to understand why it's H1 and H2 and H1, we are calling the height of the water H1, or sorry, H2, and the height of the chemical, these two heights subtracted from each other. I suppose height of the water, you have to subtract this portion, so height of the water is going to be 400 minus 50. That's what we come up with. So the difference in pressure between these 2 points, which is what we are looking for, is going to be, I'm going to leave units out of this for now, times 9.81 times 400 minus 50 divided by 1000. This is, okay, I have to put units here, millimeters per meter. And both of these are in millimeters up here. So this will get us 2 meters, because we will have meters with these two here. Alright, and this is going to be subtract 918.2. Also kilograms meters cubed times 9.81 meters per second squared times 225 divided by 1000 millimeters per meter. This will equal 1407 pascals, which is most closely correspondent to 1.4 kPa, which is answer choice A. Awesome. That is all the time I have for today, guys. Hopefully this is useful to you. I will upload this as soon as I can. Thank you for joining. This is, for me, it's personally, it's a lot of fun. So hopefully you guys find it fun too. So with that, I'll say I'll take care, stay safe, and hopefully we can continue to do this in the future, and hoping it's helpful. All right. Thank you all very much.